Welcome. Today we will be finishing up Gaussian processes. I'll just show a little demo and then we move on to something completely different. Briefly about logistics. So the new project is out on kernels and the last homework was due. The next homework will be shipped very, very soon. It's currently being tested. One thing that's important about the next homework assignment is you have to do it before the next project. So I guess we currently have project 6, that's the kernels. After that comes project 7 on trees, boosting, and bagging. For that, it will use something that we don't cover in class that you have to derive in the homework. So please keep that in mind. So if there's a project that you don't know how to do, it's probably because you haven't done the homework yet, right? So it's the question where you have to derive a linear time update for the regression tree. Yeah?
So how many projects and homeworks do we have left?
There's a lot. So there is hopefully 8 projects in total. So there's 6 right now is online, there's 7 and then comes 8. 8 is, I think it's a 90% chance that you have project 8. And there's also the Kaggle competition which will go live tomorrow or on Wednesday. And that's all set up now. We're just testing it one more time. Okay, any questions about it? Sorry?
And the homework, is this the last homework?
No, there's one more after this. So the homework that will come out now, and then there's one more after that on deep learning. And then that's it. Yeah. Any more questions? Okay, so what we did last time, let me just briefly review the high-level picture of Gaussian processes one more time before I show you a little demo. So basically what we did is we went back to this linear model where we say, well, if you want to do regression, right, and we had this linear model where y equals w transpose x plus b, and then we set some Gaussian noise. And in that case, actually, the question is, how do we learn that w? And what we've done several lectures ago, we introduced 2 different methods to learn this w. It's either MLE or map. In the last lecture, we said, well, actually, there's another alternative. It doesn't have to be MLE and map. MLE and map, what they do, they both give us one particular model w. And then once you have that model, you make predictions. MLE gives you the model that maximizes the probability of the data given w. Map gives you the probability of w given the data. And so we introduced another alternative, which is, I just call it the fully Bayesian or the true Bayesian approach, which is basically said, well, let's just get rid of the model altogether and instead just say, well, the probability of a y given x is, and the data, this here is my test point, is basically, the distribution. It's the prediction under every possible model that you could possibly have. So we say, well, for any w that I could have, I get a prediction. And every w has some probability that I would actually get it from my training data. And I integrate that out. And so if I do this, basically I'm giving you the prediction that's really the outcome of every possible model I could learn, weighted by the probability that I actually get this model from my training data. Then it turns out because everything is Gaussian, everything is just product of Gaussians, and the product of 2 Gaussians is again Gaussian. By the way, that's exactly what you had to do in the placement exam. That was one of the questions in the placement exam to prove that. What we get is this here is a Gaussian distribution. And then we said, well, why are we actually doing all this stuff? If we just know it's a Gaussian distribution, we can just fit that Gaussian distribution to begin with. And so that's where Gaussian processes come in. We basically say, all right, well, that sounds great. Right? Does anyone know how to move this thing up? I don't. Okay, that's fine. So what we then do is we say, well, actually, we can just assume our whole data is Gaussian distributed. Right? And that makes sense because in some sense, here all the assumptions we made are pretty reasonable, right? And then we arrive at exactly that conclusion. So let's just assume that, right? And basically what we're saying is all our data, all our training data, and our test data come from the same Gaussian distribution. Right? We have some huge distribution in this n+1 dimensional space. Okay? And so in this high dimensional space, we now have this Gaussian distribution. We can always assume it has zero mean just because you can just subtract the average label from your labels. Then you have zero mean. So that just makes the math easier. And a Gaussian distribution has a covariance function, right? So it has a mean, it has a covariance function. And so this covariance function is a big matrix that's n+1 by n+1. And so in some sense, what you're doing when you have such a Gaussian distribution, you can now draw labels, right? So what is, if you now draw a sample from this, that's an n+1 dimensional vector that gives me a label for every single training point and the test point. Okay? That's what the distribution does. And the important part is that these labels, they're interconnected, right? Otherwise, we wouldn't be able to do any training. Otherwise, the training data wouldn't tell us anything about the testing. And the covariance matrix, the mean just tells us an average there kind of 0. That's fine, because we subtracted the mean. That's exactly what you would get. The covariance matrix tells us how they're tied together. The first thing you have is the diagonal. The diagonal of the covariance matrix tells us for every single dimension here how spread out that is. If this entry here is small, then that means you will always get something around 0. If this is large, this entry here, the sigma of 1 of the first dimension, then that means sometimes you get a very positive value, sometimes you get a very negative value. In expectation, it's 0, right? But sometimes it's positive, sometimes it's negative. It kind of varies around, right? This one, the sigma basically tells you how much does each dimension vary on its own. And you have basically one such entry for every single one of these dimensions. And then come the off-diagonal terms. And the off-diagonal terms, here we have an ij entry. And that's really where the magic is, right? The off-diagonal terms tell us when we draw a sample, right? How correlated are they with each other, the different dimensions with each other? So what we get here is if ij is a large value here, then this means that if we draw yi, if we draw a sample, then yi and yj will always get roughly similar values, right? Because they're correlated with each other. Okay? So you can draw as many samples as you want here, right? But one of them will, these kind of go together. Okay, so it will be very rare that one is large and the other one is small, right? Because the ijth entry in the covariance matrix is large. This is kind of like, imagine these, this now goes back to the housing price one more time. These are all the houses in Ithaca or something, or in the United States, right? I and j may now be my house and my neighbor's house, right? Or two neighboring houses. So I can draw different values here. Maybe they correspond to different times where houses had different prices, but these two roughly always had very similar prices. If the ijth entry is small, if that's a 0 here, then these are not uncorrelated. Then actually, this can be large and this can be small. It doesn't really matter, right? So they're independent of each other, right? And so what you as a data scientist, what your job is, basically the first thing is you make this assumption that the data is Gaussian distributed. That's not a crazy assumption. This here proves that you're not crazy. That's good, right? Keep that around in case someone accuses you of being crazy. You're not. And so after you made that assumption, you have to make a second assumption. And that is basically what points are correlated with what other points. And that's where you bake the assumption of the algorithm in. Remember the very first lecture, right? I told you every machine learning algorithm has to make assumptions. Otherwise, we cannot make predictions. You have to assume something about your data. This is where you bake it in, right? And so one such assumption, for example, could be like k-nearest neighbors, where you say similar points have similar labels. Then you could, for example, say here the entry sigma ij is e to the minus xi minus xj squared over some sigma. So basically saying if these 2 points are similar in features, then this here will be around 1. So they are highly correlated. If they are very different, then this here will be large, so this here will be 0. So they are not correlated, right? But that's your assumption. That's just one assumption you could make. Another assumption you could make is that you say sigma ij is xi transpose xj, right? Then you're assuming that they're linearly. There's basically some line, right? So if you may have a value that's really far away, that's okay, right? that's basically you're saying there's some kind of line saying if this guy goes up, this guy goes up too. So there's a linear dependency between those two. Or you could have a periodic kernel. It actually says, you have a periodic function. Anyway, so you do this most of the time. We just use the RBF kernel just because it's the simplest, at least in this class. And then once you have this kernel function, then you do the magic. The magic is that you can actually just say, what is y test given all the other ones? All the training points and my coordinates at that. So if you now condition on everything else, that this still stays Gaussian. And in the lecture, basically, I showed you what the derivation is, what the expression is. So this here is again Gaussian distributed, right, with some value k star, where this here is k star, transpose k minus 1, this here is my k, and y. And then you have some sigma term. And the beauty is, this is now a one-dimensional Gaussian distribution, where this here is my mean, and this here is my variance. Any questions about Gaussian processes? Yeah? What is the y without any subscripts? Where is it? Oh, I see. Yeah, this is my test point. Yeah. Oh, I see. That's a long vector. y1 to yn. Yeah, good question. Yeah. So essentially all you're doing is you're putting all your data in one big, you basically make a big Gaussian distribution, and now you say, well, I know the values of all the training data, and that now gives me a distribution over the test data. So in some sense, it's not really an algorithm, right? It's a formula. Right? So there's nothing iterative about it. Yeah?
What is sigma in this case?
Sigma is so this sigma. Yeah, so this basically you have to look it up. It's the it's the closed form solution for the variance of the test point. So it's k star star minus k star transpose k minus 1 k star. So I just didn't fit in. So the reason I like Gaussian processes so much is because they give very good estimates for regression problems, and they give you uncertainty for regression problems. And that's usually hard to come by, right? If I regress something, like with classification problems, you can kind of say, well, how far am I off of the hyperplane, right? If I'm very close, then I'm uncertain. If I'm far away, I'm uncertain. I'm very certain. If I'm close, I'm uncertain. With regression, you typically don't have such a measure, right? So I estimate something, but it's not clear how uncertain the algorithm is. Right? The beautiful thing here is that you actually get these very well-calibrated Gaussian distributions, and we know, Gaussian distributions make a lot of sense to us, and we know exactly how to interpret these. One place where Gaussian processes have been used a lot is for function minimization of unknown expensive functions. And I mentioned last time the Malaysian airline. Actually, someone told me afterwards, by the way, they never found that plane, so good, algorithms can't be that great. I guess they did find it eventually, but I'm not sure. But one place where machine learning that comes in a lot is actually hyperparameter search. So think about the following problem. I have a support vector machine, and I would like to know, and one thing you will see in this project that you're doing now is that, we take a kernel function and you take your C parameter, and actually support vector machines are very sensitive to hyperparameters. So if you have the wrong parameter for your kernel and the wrong C parameter, you get horrible results. So how do you find the best results? And basically what you're doing is you try a combination of your hyperparameters, then you train the system, then you evaluate it on your validation set, and then you get a number, which is the validation error. Right? And so that's essentially what this is a function. Right? It's a function that takes as input two hyperparameters, and its output gives you the validation error. And you would like to minimize that function. Okay? And that's my favorite application of Gaussian processes. It's called Bayesian optimization, or short BO, which is a horrible acronym. And I can now show you an example of Bayesian optimization. Okay, and what I will show you, okay, I show you twice, because it's going to be, basically what I have is I have a function, I think it's actually kernel regression, that I'm solving repeatedly, and I would like to find the best hyperparameters. I have two hyperparameters, one is regularization, the other one is the kernel width, so the sigma in the kernel. And I want to now find which one gives me the lowest validation error. And I have two methods. One is to take grid search, just try out any combination of these two parameters and see which one gives me the lowest error. That's reasonable, and that's widely used. Another one is to use Gaussian process regression. And so here's the cool thing that I can do with Gaussian process regression. I can always look at the setting that is, where I'm still really, really uncertain and say, well, I don't really know, what I should get here. Or I can look at something where I know a hyperparameter setting that has worked in the past very well. And that's called an exploitation trade-off. So I can either try out new values where I'm sure that may surprise me, or I can try something that I think, well, that's probably going to be pretty good. And there's nice ways to trade these two off. And I can now show you a little demo where I put these two head to head, so next to each other. Okay, so here is my demo, and what you see here on the left is this here is my grid search on the left. So what I'm trying out, I'm trying every possible combination of sigma and lambda. This is my regularization value, and this here is my kernel width. Right? And one by one, I'm trying these different values out, and what you see here on this is actually the test error, or the validation error. Right? And I'm trying to find the setting that gives me the lowest validation error. What I'm doing here instead is I'm fitting a regression function to this. Right? So I'm trying out some random values at the beginning, and then what I'm doing is I look at more and more at values that basically could be promising. And that's the red line here. And one thing, if I show it one more time, what you see here, the surface here, is actually whether, at any given point, sigma lambda, I can make a prediction. And the Gaussian process regression tells me what it thinks my validation error will be. Right? That's the surface here. Okay? And that's not always correct, but the nice thing is it also tells me how uncertain it is. So the beautiful thing is that what you will see if I run it one more time is that the Gaussian process regression very quickly actually learns that surface very quickly, and then I actually have a pretty good idea what the best parameters are. So one more time, right? Here I start off with some random ones, and here I already know what the surface looks like, and here are the best values, right? So only after a couple of runs, actually, Gaussian process regression has already figured out what the best hyperparameters are. And this guy is still kind of, slugging away here and trying out values here. They're always terrible. Every single one of these has been terrible, right? It keeps doing it. Whereas Gaussian process regression, one thing you see is here we know they're pretty bad, right? And the uncertainty is not enough to convince us that it's worth exploring here, right? Because we know that the error here is very high, and even if the uncertainty is reasonable, this is not going to give us anything. So very quickly it learns to dig here, right? And tries to find the hyperparameters. And one thing you can see here on the bottom graph is basically the number of iterations, the number of times I had to train my algorithm, and this here is basically the best error that I got. And Gaussian process regression very quickly, arrived at the best algorithm, right? At the best setting, whereas after maybe 35 iterations, whereas only after 80 iterations did the grid search get there. Right? So that was twice as long. Any questions about this? So keep this in mind when you do hyperparameter search later on when you're in industry or something, right? And people do these grid search, you will see people do this grid search, right? It's much, much better to use a machine learning algorithm to predict you which hyperparameter setting will work well. Yeah, question?
So is it always better to use the Bayesian optimization?
Then grid search, yes. Right?
So why do people still use grid search at all?
Oh, why do people use the good question? So he's asked, why do people still use grid search? And the reason is because they don't understand Gaussian processes. That's right. Yeah?
What is the input that you give to that Bayesian? What's the input to the Bayesian optimization?
So Bayesian optimization just has a two-dimensional regression problem. the first hyperparameter and the second hyperparameter, and try to predict the validation error in that setting. That's what it is. Right? So in some sense, you put a machine learning algorithm on top of another machine learning algorithm. And the nice thing is the Gaussian process regression really doesn't really have any parameters, right? So that's why you can actually use it, right? Like if that again had parameters, then you would have to use another algorithm on top of that, and another one on top of that, right? It wouldn't work, right? There's some hyperparameters, but there's good ways of setting those. Any other questions? Yeah. That's right, good question. So the first few, it starts randomly. And then after that, it actually, then it fits the surface. And then it basically looks into what's the minimum, taking into account the uncertainty. That's the important part, right? So you may have some areas where it thinks it's pretty bad, but it's so uncertain that it could surprise you. Other areas where it's probably pretty promising, but there's no uncertainty. And then it trades off and basically looks which is the one that's most promising. And it evaluates that one, then retrains the Gaussian process. Last time actually I gave this lecture, there was someone from the medical school was actually in the audience who took the class, and he had a very interesting problem. He was like, well actually, I'm working on something that's very related. He works on hearing aids. And so what he wants to do is he goes to humans and asks them and makes these audiograms, right? These are audiograms where basically what you do is you have frequencies here, and this here is the volume, right? The intensity. This is logarithmic. Both of these are logarithmic, right? And so what you want to know is at what volume do you not hear it anymore? So blue means basically you look at this. Do I have a mouse here? I don't have a mouse. You have these. Sorry, 1 second. Here we go. Here, basically, this is the line, right? These red ones, the person could not hear. At this frequency, he or she could not hear these, and then eventually suddenly could hear them, right? And what you want to know, what he was very interested in is, how do you once you have these curves, then you can build hearing aids that basically amplify certain regions where you hear badly to kind of make this somewhat a strange line. This is actually what you want to get. So one more time, so basically up here, on the very, very top, like this is logarithmic, right? So this here is very, very loud, right? So this is kind of the volume where, if you would go to a Deadmau5 concert, right? That would be the kind of the volume of a Deadmau5 concert. And down here is not very loud at all. That's the sound that a real Deadmau5 makes. So what they currently do is they take these patients and they take a certain frequency and they slowly increase the volume and basically say something, press a button when you hear it, right? But often these are elderly people, so at some point they fall asleep, and then they don't say anything. Or, it's a very annoying process, and they have to actually try every one of these tones multiple times, because actually right down this threshold, you actually hear it half the time. Actually, right when your heart beats, you don't hear it, and then your heart is not beating, you do hear it. It's like, anyway, so what he wanted to do is actually want to use Gaussian process regression. And so the idea was basically, instead of using this grid, which is the FDA-approved way of doing it in the United States, can't we just actually always kind of find the optimal tone that is most informative? And so we actually started a research project with this together, and it turns out you can do this very well, right? So the first thing what it does, it plays this tone, you hear it, and this here is the current threshold, and then you keep playing tones, and only after 15 tones, right? Usually you subtract them to 100 tones. After 15 tones, you're already much more accurate than anything that was any previous technology it could have given you, right? And one thing we also realized is really, really cool is with tones, you can actually play 2 tones at the same time and then see if they hear something or if they don't hear anything. It tells you something. And so actually those guys now went off and actually, this person actually now is commercializing this as a hearing aid system. Yeah?
So doing this, like you kind of combine 2 things in a way that I'd like you to, if you could justify that exposure that you're not just using the Gaussian process regression to find hyperparameter parameters for your generalized, classifier. It's that you are actually generating your data points using.
That's right. The same with the hyperparameter. Yeah, that's right.
And so you're going to actually generate data points in the manner specified by the algorithm. Is that a closure way?
Well, it Passover has passed, so it's a slightly different problem. It's called an active learning problem, where you actually generate your own data, right? So it's basically you get a new data point, now you get a label for it, and you basically try to find the decision boundary, right? It's called active learning. So it's totally fine. And in fact, actually, it can speed up your training a lot, especially when labeling points is very expensive. I can show you this one more time here in the, and I think is this the demo? Yeah, so this here is basically the demo where you get a bunch of data points, and now I fit my function, and now I want to say, well, where is, let's say I want to find the maximum instead of the minimum or something. Well, maximum is probably around here, but it could also be here. So maybe add a new data point and get that labeled, that's maybe here, right? And so then I get this value, etc. Does it answer your question? Okay, any more questions about this? Oh, actually, I have one more warning to you, actually. The Gaussian processes are awesome. And if you do regression, I would always recommend you do Gaussian processes. They're extremely accurate. In fact, they're so accurate that they actually became illegal in North Carolina. And I'm not joking. Here's actually, this morning, I'm proud to have found the legislature that actually outlaws Gaussian processes in North Carolina. And it's actually, it's a proud moment. It's in the context of global warming, of course. So basically, people used Gaussian processes with nonlinear kernels to predict the sea water levels. So North Carolina is on the coast, and people had to predict, it's very important to know where the sea water levels are going. If you take these nonlinear algorithms, not only, you basically get a very good prediction of where your sea water levels are going, but you also get uncertainties. So you can actually say, well, it's at most that bad, or it's at most that good, etc. And unfortunately, that was still too bad, and people didn't really believe in global warming. So they couldn't really do anything about the data, but they could do something about the algorithms. And so they actually passed this law. This is from 2011. This is a while ago, but it's still active. And actually shows here that, so if you do predictions on sea water level rising, these rates shall only be determined using historical data. This is fine. And the data should be limited to the time period following the year 1900. That seems fine. Rates of sea level rise may be extrapolated linearly. So you're not allowed to use nonlinear algorithms to estimate future rates of rise, but shall not include scenarios of accelerated rates. That's the nonlinear thing. So no matter what your data looks like, right? Even if it, has this very clear elbow structure, which it does, right? So basically the temperature goes up, right? Like this, you have to draw a line through it and can tell your voters, no problem, nothing is happening. So please keep that in mind when you use Gaussian processes in North Carolina. And don't go to the bathroom. All right. Okay, and now for something totally different. All right. So one thing that the Gaussian process essentially is a nearest neighbor algorithm. And it's basically a linear algorithm, linear regression that we kernelized. Kernelization always reduces bias. And then essentially what we arrived at when we use the RBF kernel is something that's very similar to the nearest neighbor algorithm. So what I want to do is spend one lecture on the nearest neighbor algorithm. And there's a good reason why I will do this. You will see it next lecture when we go back to this. Or when I, build on top of it. And what I will briefly review is KD trees. Has anyone heard of KD trees? Raise your hand. Okay, very few people. So here's the problem, and I will give you notes in a few minutes. And K-nearest neighbors is a very slow algorithm. And why is it very slow? Because what you have to do is you have all your data points. And what you need to do is you need to find the nearest neighbor, right? let's say this here is my test point. I don't know the label of this guy. And in order to find the nearest neighbor, what you need to do is you need to find the distance to every single one of these points. And then you find the minimum, and that's the nearest neighbor. All right? So imagine I would like to find out who lives closest to me, right, in Ithaca. I guess most of you probably live in Ithaca. Well, so one thing I could do is I could go to the first person and say, where do you live, right? Compute the distance, right? And then go to the next person, where do you live, where do you live, where do you live, where do you live, right? And eventually, basically, at the end, I take the minimum, and that's my nearest neighbor, right? Seems rather slow. A much faster way could be if I before and say, well, I live in Bell-Sherman. I don't know if you guys know the different parts of Ithaca. Does anyone else live in Bell-Sherman? Raise your hand. Well, I didn't think so. All right, it would have made it too easy. Who lives on North Campus? All right, who lives on South Campus? Can you live on South Campus? Does that exist? Well, so basically people on North Campus, they're pretty far away from where I live, right? So you guys can probably, I can probably rule you out. And so one thing you could do is basically look in the beginning at the global structure of the problem and say, well, I have a good hunch, right? People who kind of should be my nearest neighbors, they're probably, roughly close to me. Or another way, let me put it another way. Like one way to speed up nearest neighbor search by a factor 2 is if before I do this very simple pre-processing step, where basically draw a hyperplane that divides my data in half. Okay? And I do this at the beginning when I collect my data. And now what I do is I have my test point, and the first thing I do, I look for the nearest neighbor only in the half that I'm in. And I do this, and I find the nearest neighbor. It's this point here. Okay, this is my nearest neighbor. And I make an outrageous claim. I claim that once I found this nearest neighbor, which is the nearest neighbor of all the points in here, I claim I don't even have to look at any one of these points. Why not? Who can tell me why not? It's not a trick question. Yeah?
Because the other points are farther away from that point than the halfway line. So you definitely know they're farther away.
That's right. So the other points are at least that far away. And that's already further away than the point that I already have. Right? So nobody can be closer than the neighbor that I've already found. All right? So I don't even have to look at any of these points. Yeah? Any other questions? All right, good. You got me. He said, well, wait a second. You cheated. Just draw the point right here. What if the point is right here? Right? And in that case, you have to still look. Right? And so the argument is basically, well, most of the time, this won't be the case. And then you're lucky. And occasionally, you just have to do as much work as you would have to do anyway. Right? So that's not a big deal either. Right? So you either get a speed up or you don't. But yeah. Sorry.
Chop your data into half, like over and over again.
All right. That's exactly where we're going. That's right. Any other question? You had the same question? Okay, good. Right. So then, of course, comes the second question. Well, if we can do this once, right? Why can't we do this multiple times, right? So we could, for example, now say, well, we split it up like this, and then we split it up again like this, and here, and then on the right-hand side we split it up like this and like this. We split up like this and like this, and so on, right? And so you basically have little boxes, right? And what you do initially, you just find the nearest neighbor in your box, and then you try to rule out the other boxes. Okay, that's the high-level idea behind KD trees. That's exactly what we're doing. Any questions about the high-level idea? Okay, so here's the first quiz I have for you and your neighbor. Imagine I have the following. I have a test point. This is my test point, xt. I have a previous nearest neighbor. This is my previous nearest neighbor. And I claim that this point is closer to my test point than this wall. Now I have another point here that I haven't looked at anymore. Can you prove that this point here must be further away than this point. Okay, does it make sense? So I basically have my xt, I have my presumptive nearest neighbor. Now comes one more candidate over here. The only thing I know about this point is that it's on the other side of the wall. Right? The wall divides the entire space. Can you prove to me, because you have to be mathematically rigorous, right? So if you do this kind of stuff, can you prove to me that this point must be further away than that point? Right? Provided that the wall is further away than xp. As I give you a minute, see if you can formally derive it. I mean, I know it's obvious, right? But we have to be rigorous because the next steps will be less obvious. So, all right. Who thinks he or she has proof? Oh no, if you can't prove it, you can't use it. Yeah.
So if you draw the projection of the target point on the line that links
this point? Yeah. That's a projection onto the plane? Oh. Oh. Okay, good. I like this.
So we know that the density that the point is closer to the target point. The projection is the closest possible. The projection is closer than the point. Right?
This point is closer than that. Yes, yes.
Then we can prove that the wall lies on that same line. Because it's the projection.
Yeah, I think you're going in the right direction. That's definitely a way to prove it. That's absolutely right, actually. Let me just do one that's even simpler with the notation that I drew here, but you're definitely right, right? Because basically the distance from xt to this point here is c plus d. All right? Now, I claim this theorem by this guy, I don't know if you heard of him, Pythagoras. C squared equals b squared, a squared plus b squared, right? So c equals the square root of a squared plus b squared. And then we have d. Well, this is certainly, greater than 0. So we can just, one thing we can say back, and that's greater equal than just the square root of a squared plus d. Right? Well, that's just a. And this here, so this is a. A plus d. D is also a positive thing, or non-negative thing. So this is greater equal a. Okay? So c plus d is greater equal a. So it's greater than this. And a is greater than the distance to the nearest neighbor. And that completes the proof. Anyone spot a mistake? No. Okay. Any questions? All right, awesome. So the important thing is we didn't actually use anything particular here. One thing we used here is that we used Euclidean distances. Right? So we made an assumption that it's a Euclidean distance. Okay, I can now give you the lecture notes.
Yay.
It's a lot of excitement for this lecture. I'm glad. All right. So the goal is to speed up nearest neighbor search. And we basically partition the data repeatedly into half. And so the idea is the following. At the beginning, when we have our data, we build a data structure. And then hopefully we can use this data structure just later on during test time to find nearest neighbor really, really efficiently. Quick thing, who did not get a printout? Oh, sorry. The printer broke during printing. So this is all I got. The notes will be online, though. They already are online, actually. So maybe those, if someone has, if someone and their neighbor they both have one and you get along with your neighbor, maybe one of them, you can pass them back to those people in the middle. All right. So let's say we have this data set. And I now tell you how to set up this data structure. And the data structure is a tree. Right? So all those computer scientists in the room, you will now be relieved, right? Finally, something from computer science. So you guys all know trees really, really well. And the idea basically is we build a balanced tree where every single node, every time we split the data set in half. So here's the idea. It's quite simple. The algorithm is as follows. We just take, the first thing we do is we take one dimension of our data. And it doesn't really matter which one it is. Typically, what I recommend is take the one with the largest spread. So you compute the variance in each dimension, and you take the one with the largest one. But you just use a heuristic. Another option is to rotate through the dimensions. Typically, variance works better. So in this case, let's say we take this dimension. What we do is we find a splitting point such that exactly half the data points on one side, half the data points on the other side. That's easy to do. We just look at this one coordinate. We just find the median. Okay, we split along the median. So now we basically have this thing here. This is my first splitting value, t. And my dimension is 1, right? So x1. So then you basically take your data. Initially, all your data is in the first node. And then you say we have built two subsets, right? The left and the right one. So you basically say, is x1 greater than t? Like, yes or no? And now you get two new nodes. Does that make sense? Raise your hand if that step makes sense. Okay, awesome. So I take all my data, I find a splitting point, which is find a direction, so a dimension. For example, the dimension with largest variance. I find the threshold, which is just the median. That's very fast to compute. I just say if you're larger than the median, go to the right. If you're less than the median, go to the left. And then here, I just run the algorithm again, recursively. Right? I find some other value. It could be the same value. And again, I keep splitting. So let's say, for example, here, I split again along this direction, or here I split along this direction. This is my first one. This is my second one. My first split, my second split. Now we have, for example, x2 greater than t, t2, 1 or something. x1 greater than t2, 2 or something. Another threshold. And then these are my leaves. So these are the final boxes that I end up in. And this is all there is to it. So it's a very, very simple algorithm to find such a data structure. And now how do you use this during test time? Well, during test time, any questions about how to create this structure? So at the end is a balanced tree because you always split everything in half. And all your data actually is in these things at the bottom, in the leaves. And every data point can only be in exactly one leaf. All right, so how do you now do testing? And it's quite simple. What you do is you take a test point, and you basically descend into down the tree, right? You say, like, on the first dimension, am I on the right side? Am I on this half, or am I on this half? And if you're on this side, you go down here. Then you say, okay, my x1 is larger than this threshold or smaller. If it's larger, then I go here, or otherwise I go here. Right? So you basically just look into which of these leaf boxes do you fall. In this case, we have these 4 leaf boxes. Okay, so you fall into one of these boxes. And then what you do is, let's say I end up here. Then you do a nearest neighbor search in this box. Well, that's very fast because you have very few points in these boxes. This tree can be pretty big. Going down that tree doesn't take very long. How long does it take? I heard it. Log n, right? Log n time. It's O log 2n, right? What's log n? It's 30, right? So no matter what your n is, log 2n is pretty much always less than equal 30, right? Because we never work with numbers that are larger than 2 to the 30. That's ridiculous, right? I mean, even if you're 31, that would be twice as large, right? Or 32, that would be 4 times as large. Like that, you never see that in computer science, right? So that's basically, that's for all means and purposes a constant. Okay, so you go down here, and you end up in one of these leaves. You find the nearest neighbor. You're pretty good about yourself. Now you're not sure yet if this is your nearest neighbor, right? You haven't looked at all of these data points yet. So what do you do now? Who knows depth first search? Raise your hand. Okay, this is just depth first search. So you go down, into this one of these. Let's say I end up here. Then what you do is you back up one, and at this point, let's say I fall into this bucket here. I find my nearest neighbor here. That's this guy. Now I go one level up. What is this level up? That's exactly this decision boundary. And here is where I do the pruning. So here I say, I've looked at all these guys. I found my nearest neighbor. And I go one up. Is it worth going down here? Right? And when is it worth going down here? Only if the distance to the wall, to this threshold, is less than the distance to my current nearest neighbor. If these points are all behind the wall, right? If these points are all further away than my nearest neighbor, then I don't even have to go down here, right? I can just prune it. Then I go one up. And again, I have a whole subtree that I haven't looked at yet. And once again, I look into, are these points further away than my current nearest neighbor, yes or no? Right? And if no, then I just prune the entire subtree. And if yes, then I go down here, and I go down and I basically, run the algorithm over and over again. Any questions about the algorithm? Yeah?
Every level we are only looking at one dimension of the data.
Yeah?
How can you ensure that considering all the dimensions of one is still close?
Sorry, one more time? How can we?
Ensure that considering
well, you're basically bound, right? You basically say, so he's saying you're just looking at one dimension when you look at this wall, right? But that's enough, right? And sometimes you say, if in that dimension you're already that far away, right? If I look at the other dimensions, you can only get further away, right? So if you're already too far away in that one dimension, then I may as well just, not look at you. Okay, does that make sense? Okay, last question, then I have to quit for today. Yeah?
How far do you have to subdivide your data? Because the more levels your tree goes, the quicker
Right. We will get into that. I'll show you this next time. So it depends a little on your processor. So usually what you want is that these are all in your L1 cache. Yeah. Okay. See you all in 2 days.